Assalamualaikum. In this session, we're going to learn basic two-dimensional NMR spectroscopy, or known as 2D NMR spectroscopy. Let's refresh the basic principle of NMR. Proton NMR spectroscopy provides information about the environments of the proton atoms in a molecule, and the same principles apply for the C13 NMR. When the nucleus has a spin half, so when it placed in the strong magnetic field, it can exist in a higher or lower energy states. When the nucleus has been irradiated, it will absorb the radio frequency radiation, and the nuclei in the lower energy spin states are promoted to the higher energy space. The difference between these two energy produce a signal. There are important difference between proton and C13 NMR, where the signal for proton NMR are more sensitive because it has 99.998% abundance in naturally, and the proton NMR spectra can usually be measured by a single stand compared to the C13. As a result, the peaks are proportional to the number of hydrogen atom, and it is very useful when analyzing the spectra. For the proton NMR, for each signal, it contains three important pieces of information, which is chemical shift. Chemical shift tells the environments of the proton. Integration, it tells us the number of protons, and the splitting pattern tells the number of protons on the adjacent carbon. This is the scale for the chemical shift of the proton, where the smaller number is for the shielded proton, and when it goes to the higher number, it is become more de-shielded. The basic principle for the C13 is same, but is a low sensitivity. Why? Because only C13, 1.1% of C13 presents naturally, and it is a magnetic moment is in C13 4 times weaker than proton H. That's why the signal for the C13 is 6,000 times weaker than the signal for the proton H. That's why they use the Fourier transform NMR 30,000 pulse, so it can make it more high resolution. The information for the C13 signals appear in the chemical shift in the range of 10 to 200 ppm. And in the C13 NMR is 20 times more resolved than proton NMR. The same principles apply for the C13, whereas the lower number is for the shielded and the higher number is for de-shielded. The chemical shift apply the same principles, where the signal of shielding and de-shielded are in the same region, which is up and downfield. Now, the first term, we comes into the first term of 2D NMR. The first term is depth C13 NMR spectra. Normally, we only hear about C13 NMR spectra. All the carbon will appear in the C13 spectra, including methyl carbon, methylene carbon, methane carbon, and quaternary carbon. In depth C13, the purpose of depth is to differentiate between all these 4 types of carbon. For example, in depth 19, this is the experimental had been set up in the instrument. Depth 19, we can see only the CH peak, and in depth 135, we can see the CH2 peak and CH and CH3 peak. This H2 peak is fall in the negative part, and this one will fall for the positive peak. Let's see the example here. And before we go for the example, let's know what is the full name of depth. Is stand for the distortionless enhancements by polarization transfer. this technique to distinguish CH3, CH2 and CH group. For example, in 2-butanol, actually there are 4 signals for the carbon, and normal C13 NMR we can see 4 signal, and in depth 1, 3, 5 we can see only 3 signal. In depth 19 no signal because there are no CH. In depth 1, 3, 5 we can see these 3 signal. Positive we have CH3 appear the up positive side, and CH2 become down, which is CH2 side. Let's see the clear about the spectra. So in this case we take one example for this structure. Subspectrum, this one is spectrum A. It shows the presence of CH for this structure. Only 3 CH appear. This one is depth 90, and this one is depth 135 degree, which is 3 CH and 2 times CH3. So total will be 6, right? So here 2, 4, 5. Sorry, this one is total 5. 3 times 2 become 5. So 1, 2, 3, 4, 5. This one is for CH and CH3, the positive side. The negative side is for the CH2 for this structure. This one depth 135. For total signal here, how many? These all CH include. For normal C13 carbon, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All total is 10 carbon. So now is 8, 9 and 10. So that's correct. Why only this appear 5? Because some quaternary carbon are not appear in depth 135. Why only appear 3? Actually the 10 carbon appear in this structure because this one only CH appear. That's that C13 NMR spectrum. This called is one type of 2D NMR. Next we go for another type, which is Cosy. Cosy means correlation between proton and proton. In the 2 NMR we can see the correlation between proton and proton, and in the 2D they have x-axis and y-axis of the spectra. And proton coupling you can show in the diagonal correlation. In the middle we can see the correlation with different spot, and this allow for us to determine the correlation between protons in the correctly positions, and will help us in the assignment for the structure. Let's see the Cosy spectrum, and this is the structure for example. And we can see how we can know whether this proton correlate with this proton correlate with here, this proton correlate with here. So we can see in the Cosy spectrum. This x-axis is proton, this y-axis also proton. We want to see the correlation between proton and proton. Both spots are same. The above part and the below part is same. So means this line here is like a mirror. You can see the above part or you can see the below part. It is same. Okay, you can choose whether you want to see above or below, or you can see both. Actually both are same. Here we can see A is correlate with B. Here also A correlate with B. So this is one rectangular square. I always draw the rectangular square, so I can know only one we consider as a correlation. In this case they have how many spot? 1, 2, 3. Means in this structure they have a 3 correlation between proton and proton. We see what's the correlation is A and B. Okay, correct, because A and B is a proton neighboring each other. In the Cosy only neighbor proton can correlate each other. It cannot goes more than one bond. Means A cannot correlate with D, A cannot correlate with D because it's more than one bond. So only one bond can correlate each other, the proton. This is the rules of Cosy. Same goes to this one. C, it will correlate with the E. Check in the spectrum. Is it correct? C, this is a spot, C correlate with E. Yes, because this is a one bond carbon, so this is direct correlation. It cannot correlate A with E, cannot. It's more than one bond. Next, E is correlate with D, correct? E correlate with D. So E correlate with D. Another one spot. So only 3 spots appear, and so this is the structure, correct? The correlation. Next example, we can see C should be correlate with B, A will correlate with B. So only 2 spot. Here 1 spot, B to C is 1 spot. So correct, this is 1 spot and this 1 spot. Actually they have spot here, dark spot. This line we make by ourselves, the no line. In the normal spectrum for Cosy, only spot in the middle appear. This line we need to draw by ourselves. This is the Cosy. We go for the next term, which is the correlation between proton and carbon-13. And the few terms we normally use Hsqc, HMQC, and HMBC. What is Hsqc? Hsqc is correlation between proton to carbon-13, direct correlation. HMQC same like Hsqc, but it can shows us the correlation between N15. The HMBC is correlation between proton and the carbon for several bond correlation of proton to carbon. This one is more than one bond. This one is only direct correlation. Let's see Hsqc. Hsqc stand for the heteronuclear single quantum coherence. For the correlation between hydrogen and carbon, two-dimensional plot we always plot. It can be either proton spectrum in the x-axis or y-axis. It can be either C13 in the x-axis or y-axis. So we can see the spot in the middle. It shows us the correlation between proton and carbon based on the spot. And we can see the connectivity of the carbon and proton in the molecule. That's why the structure will be established. See the example here. The x-axis, they show us the carbon-13, and the y-axis will be the proton spectrum. Normally what we run is the x-axis will be the Proton NMR and the y-axis will be the carbon-13. It can be either one. Both, the important part is the correlation in the middle here, because in the Cosy, in the Hsqc, what it tells us is correlation between proton and carbon. Only direct correlation. If proton A is direct correlate with the carbon A. If proton B is direct correlate with carbon B. So here we can see A is carbon A, direct correlation. B is carbon B. C is carbon C. Proton C is carbon C. Proton D is carbon D. So only is direct correlation. So they have 4 spots here. Next example is the next terms is HMBC spectrum. HMBC stand for heteronuclear multiple bond CH correlation. In this case, we can see the correlation between proton to carbon-13 more than one bond is over several bonds. Typically over 2 or 3 bonds can see. More than that normally is impossible to be seen. Can be used to establish connectivity across barriers such as oxygen atoms or quaternary carbon. Normally normal correlation we cannot see if the presence of oxygen. In HMBC we can see more than if we have oxygen or quaternary carbon. Means it more than one bond or 2 bond. Let's see the example for HMBC. Just now in Hsqc we only can see if 1 proton, only 1 carbon. In this case 1 proton, it can be many carbon. Here let's see H8. Example H8. So this spot, 1 spot. This is H8. This 1 spot, 2 spot, 3 spot. Okay, so in this case, it shows us H8 is correlate to the C6 and C1. C6 and C6 is here, C1 is here. Either they are not labeling, so we want to show you this proton have many spots on the line. If Hsqc, this spot only here, this spot may be only one, this proton only one spot in the middle. That's the difference between HMBC and Hsqc. Let's see the example of H9. H9 is direct correlate, is not direct correlate, is correlated with the C1 and C3 and C4. Here this one is C1, C3, and then maybe this one is C4. They are not labeling. That's the show is more than one spot. That's the difference between HMBC and Hsqc. Let's come to the example. If the question only given for you like this, the given the structure and the proton NMR, and then they give you the C13 NMR, and they ask you to assign based on the Cosy spectrum and Hsqc spectrum given. Before we start, we have to label first what is the proton for the proton spectrum here. Which one is H1, which one is H2, 3, 4, 5, 6, 7, 8. So based on the chemical shift, I have labeled it. This one H8. H8 is a more upfield. Why? Because it's a shielded. It's far from the CO, so means the chemical shift is more upfield compared to this H3. So that's why this one is H8, this one is H1. How I know this position, which one is H1, H8? Because of the chemical shift. Normally, the chemical shift for the methyl group, methyl proton, is around 0.821. So that's why this only 2 for the methyl. Methyl is CH3. That's why, which one? In this structure, they have 2 CH3. H1 and H8. Which one I should label as a H1, which one I should label as H8. That's why based on the structure, I see which one is more shielded and de-shielded. How do I know? The distance between this CH3 and this CH3 to the C double bond here, C double bond O here is more longer than here. That's why it is more shielded for CH3. That's why it appear in front side. That's why I labeled it H8. And this methyl is near to the CH2, so it become more de-shielded. That's why it become H1 here. And then next followed by the hey, we have another CH3? No, only these two. So now assign for the CH2. How many CH2 we have? 1, 2, 3, 4, 5. We have 5 CH2. Which one should I label? This 5 signal. This 4 1 signal have been overlapped here. So this 5 signal, which one will be H7, H9? That's why we need to see based on the attachment to the C double bond, how far they are from the C double bond. The more far from the C double bond O means they are more shielded. That's why I label it. This one is H5, H5, H7, 6, 5, 4, H5, H7, H6, H4 and H2. H4 and H2 is near to this one, so they become more de-shielded. H5 and H7, why is not directly sequenced? Because in the 2D it becomes zigzag, so the one is at the below is more have the influence by the C double O. That's why the sequence is H5, H7, H6. It's not in the sequence H6, 7, H7, 6, 5. No, not like that, because of the zigzag structure. After we confirm the level of Proton NMR, then we can go for the Cosy. We can do the assignment for Cosy. This is the question provided for you. This As I just said just now, there are no line. For the example given in the slide, for teaching, they have a line here because they already done the line for you. In the raw data, it look like this. This one is the H proton spectrum, and this also is proton spectrum. And the correlation, how we can know? The first step we should do is draw a line in the middle. Take a ruler and draw a line here, and then both side of this spot same. Either you want to see the below one or the above one. What I prefer to do is I make a square, triangle square. So I'm not confused which one is, because both are same correlation. So I prefer doing a square. So after draw the line here, I will put one square because this is one square. One square is correlation between H6 and H4, and another square is the blue color here. So this square is a correlation between H1 and H2. The next square is the correlation between H6 and H5, and the smallest square is between H5 and H7. So how many spots we have? Actually 1, 2, 3, 4. So we have 4 square here. 1, 2, 3. We have 5. 1, 2, 3, 4, 5. H8 and H7. Green, blue, turquoise, orange, and black color. So 5 spots. 1, 2, 3, 4, 5. So we can see 1, 2, 3, 4, 5. So means in our structure there are 5 correlation. After this we bear in mind. After this we check with the structure. Now go for the assignment for Hsqc. How we can do? As I mentioned earlier, the x-axis can be either based on what they are given for you. Normally they will give the x-axis as a proton and a proton spectrum, and y-axis will be the carbon-13 spectrum. So direct correlation, just make a line here and direct here, proton here direct with the carbon, and just make a line. This proton is direct with this carbon, and this one draw by using a ruler like this. So based on all this assignment, and then you know this H8, because there are no label here, so automatically this one is C8. You already label the proton H8, H1. When H1 correlate with this one becomes C1. H5 correlate with this one becomes C5, and H7 correlate with here this carbon, so automatically this one becomes C7, and H6 correlate with this carbon and we label as C6. H4 correlate with here, we label as C4, and H2 direct correlate with the DC, and we label it as C2. After the full assignment of Cosy and Hsqc, now we can put the information in the table, empty table given. So assign the C1, C2, C3. Just read based on the Hsqc. We just read the chemical shift and written down what is the chemical shift for all different C assignment, and then put the information of the Proton NMR based on the correlation, and then we check whether they have 5 correlation or not in the Cosy. So we can check 1 correlation, 2 correlation, 3 correlation, 4 correlation, 5 correlation. So in this case, why only H1, 2, 1, 2, okay, 1 correlation, 4, 5, 4, 5, 1 correlation, 6, 7, 6, 7, okay, here have 1, H7 missing here, so here also should have 5, so here is missing. Put it as a H7, so we can see here 5 correlation in the structure, also 5. In the spectrum also we can see 5 spot in the Cosy. Okay, that's all how we can solve the 2D NMR problems. Hopefully you can enjoy learning 2D NMR. Thank you.